Hello. An autoencoder is a dimensionality reduction technique based on a deep neural network. First introduced by Bardi and Hornick, 1989, and improved by Hinton and Salakhutdinov, 2006, toward the generative model by applying the greedy layer-wise pre-training technique. There are a lot of information here. I will explain in detail. Using an autoencoder, one can transform high dimensional data into low dimensional one. Okay. Hence, which means that, well, for example, if we have like this type of high dimensional data, so like we have n observation and k features, then through autoencoder, we will reduce this one into basically something like same number of observation, but something k prime. Here, k prime is less than k, so low dimensional data, something like this. Okay, so using an autoencoder, one can transform high dimensional data into low dimensional ones. Hence, a well-trained autoencoder represents an original data closely while ignoring its signal noise. So autoencoder basically reproduces original data. A good autoencoder reproduces original data without its noise. An autoencoder contains a small central layer called code that connects two bigger multi-layer neural nets on both sides, similar to a butterfly wings. Okay, we can see the image of autoencoder. So autoencoder, if we Google autoencoder and then find image, good. So yes, I think this is well, okay. I think this is nice. So this figure, we can look at this figure. Okay, let's look at this figure. Okay, so we have a typical autoencoder. So we have a small code here, and then two deep neural network at both sides. Okay, so an autoencoder contains small central layer called code. Okay, code here, small code, and then code connects two bigger multi-layer neural network on both sides, similar to butterfly wings. So here, so code connects two multi-layered neural network, left and right. Okay, so we have code, and then we have two multi-layered network over here and over here, like butterfly. Okay, and then so connect the two bigger multi-layer neural network on both sides, similar to butterfly wings, such that one wing is called encoder and the other is called decoder. Okay, so we have two wings over here. So one wing is called encoder. Encoder, here information flows in and then danced. Okay, code and then information go out through the decoder network. Here we have output. Okay? Since the input layers have the same number of nodes, since the input and output layers have the same number of nodes, so here, basically, input layer over here, and then output layers over here, they have the same number of nodes. or equivalently same number of perceptrons. Okay, stay the same. Therefore, here on autoencoders receive the high dimensional input data at one end and reproduce them at the other end. Moreover, since an autoencoder does not predict a target value, but just reconstruct its input, okay? So autoencoder receives information here and reconstruct information here, output. Therefore, it is unsupervised learning. Since an autoencoder does not predict, it basically does not predict a target value, but just reconstruct its input, an autoencoder performs unsupervised learning and then therefore does not require a labeled data. Hinton and Salakutdinov describe an autoencoder as a nonlinear generalization of principal component analysis that uses an adaptive multi-layer encoder network to transform a high-dimensional data into a low-dimensional code and a similar decoder network to recover the data from the code. Okay, we already run the PCA, so it is a bit similar to PCA, but PCA principal component is a linear model, but autoencoder is a non-linear model. Okay, and then similar to PCA, it transforms the high dimensional data into low dimensional code at the center, and after the code, a similar decoder network to recover the network, the data from the central code. Now we know the architecture of autoencoder. Then the next question is how to estimate or how to train an autoencoder. To train an autoencoder, one first assign random weight to the two networks at each side of the smaller center layer, which is again code. Okay. So first we assign just a random number. And then one minimize the difference between original data plugged into input data and reconstruct version processed from output layer. Okay, so here, so this one. So how to estimate this one? So first we assign the random number, then we plug data at input, okay? And then this plugged data goes through this autoencoder network, and then it comes out over here, decoded data, okay? And then what we do is basically we compare this input data and then we compare this output reconstruct data. We compare them each other, input and output, and then we want to make output data as close as possible to input data. So the distance between output data and input data, we aim to minimize the distance between input and output data. That's our goal. Okay, that's how we estimate the model. That's how we train autoencoder. Okay. However, in practice, that is very straightforward. However, in practice, that is easier said than done. Since multi-layer, multiple hidden layers, like a deep neural network, autoencoder in particular, it has deep neural network, each side of the code. So we have two multiple hidden layers, okay? Two copies of multiple hidden layers. So since multiple hidden layers are usually untrainable, they are very hard to estimate. Therefore, Hinton and Salakutinov recommended, they suggest a strategy how to estimate the model. First, they recommend pre-train the network. Then how to do pre-training? They recommend pre-training procedure such that train two adjacent layers, two neighboring layers, which is called restricted Boltzmann machine, and proceed layer by layer. Okay, so what it means is that, well, estimating this entire network or at once is extremely difficult. So what Hinton suggested is that we have input, so we estimated this piece first. Okay, okay. So we have this input and this one. So we estimate this one first. If we only look at this part, it is called restricted Boltzmann machine. Okay. Once this part is pre-trained, then we move to the next piece. We train this piece. Okay, of course, we use input data over here and estimates. And then we use input data over here and estimate. Actually, we have output image over here, so we can estimate. So we can use both of them. Then we pre-train this part, and then we pre-train this part, and we pre-train this part, and we pre-train this part. Okay. Once this pre-training process is over, next, we fine-tune the model by directly comparing this output and this input data. Okay. So, okay. So they recommend the pre-training procedure. They train two adjacent layers, which is called restricted Boltzmann machine, and proceed layer by layer estimation. Proceed layer by layer estimation. Once the pre-training stage is finished, a full autoencoder network is unrolled. We put together the piece by piece, okay, two adjacent layers, then it becomes a full unrolled autoencoder network. Then you can simply fine-tune the network. Next, mathematically, estimating an autoencoder network is formulated like this. We have f function from x to y and y to x. And x hat is basically a compound function, g circle fx. And then our goal is to estimate f and g. F and g basically they are the solution of minimizing the distance between x and x hat. Okay. In the equation here, X is the input space, okay? And then F is encoder because it moves from X to Y. The dimension of Y is smaller than dimension of X because it's dimension reduction technique. And here G, which is a function from space Y to space X, is a decoder. And here we have a D function. D indicates a distance. In sum, therefore, an autoencoder is an unsupervised learning technique in the machine learning field where the number and shape of the output nodes are the same as the number and shape of the input node. Okay, then what is the advantage and what are the applications of the autoencoder? Let's look at that, especially with the focus on finance. Dimension reduction technique like an autoencoder facilitate noise reduction, classification, visualization, data storage, and generative approach. Generative means it is similar to simulation. Okay. Dimension reduction aims to represent the data in high dimensional space at a low dimensional space. As we learned, principal component analysis, PCA, is the best known dimension reduction technique, but an autoencoder excels PCA in classifying and interpreting clusters in the original data, groups in the original data basically. Furthermore, when the cosine of the angle between two vectors, as you know, it is like a linear algebra, but when we measure the distance between two vectors, of course, we can use Euclidean distance. Another way is you can measure cosine between the two vectors. That's another way. Anyway, when the cosine of the angle between two vectors is used to measure similarity, an autoencoder outperforms latent semantic models analysis, LSA, a well-known document retrieval method based on PCA. Furthermore, autoencoders are also, they outperform local linear embedding or least nonlinear dimensional reduction algorithm. Actually, I did some research with autoencoder. Uh, my research is basically classifying forms to define new industry. Okay, so we extend basically my research extends these findings about autoencoder by applying an autoencoder in reducing high dimensional features of the form. You know, a form contains a lot of information, like a big data about a form you can imagine. Okay, and then because we have a lot of features, a lot of information of the form, high dimensional features of the form, we can condense it to low dimensional ones. That's what I did in my research. So reducing high dimensional feature of the forms into low dimensional ones. And then once I make form information like low dimensional, okay, and then I can classify forms based on the low dimensional, okay, then classifying forms into interpretable sectors. If I do clustering analysis or group the form into several groups, then we can interpret each group as a sectors on industries. In line with the prior literature about autoencoder, my industry classification of the forms is quite interpretable and intuitive despite small loss of information, because the autoencoder we use allows us to utilize the sparsity of the hidden layers when the model is trained and applied to nonlinearity problem beyond the PCA approach. So we can capture rich information in the data that simple linear PCA approach cannot. Okay. In addition, an autoencoder can detect anomalies well. Anomalies means like noise, for example. So like outliers. So using autoencoder, we can detect anomalies. For example, while an autoencoder reconstructs original data, some data points could show large reconstruction errors and are regarded as anomalies. Okay, so remember a autoencoder. So we plug input data at the input layer, and then we have reconstructed data at output layer. So we can compare input data and reconstruct the output data. And if we compare input and output, some data may be similar, but some data point, some observation, they are maybe very different. Input and output or constructed data, input data and constructed data could be vastly different. In that case, we can regard that data point as outliers, basically. That's the idea. Then how do you use that information about outlier? In finance, outlier is actually very, very important. Okay, so we will see. For example, while an autoencoder reconstructs original data, some data point or some observation could show large reconstruction errors and are regarded as anomalies. Therefore, to extend this intuition, Misra et al. 2020 used an autoencoder to detect anomalous credit card transaction. Okay, so input credit card transaction and output reconstruct credit card transaction, and if they are very different, they regard that anomalous and then deem them fraudulent. So using autoencoder again, by comparing input credit card transaction and reconstructed credit card transaction, if they are vastly different, then they are possibly fraudulent transaction. Their approach is basically two steps such that first, an autoencoder reduces the dimension of the transaction attributes. And second, classify transaction into clusters based on the feature vectors of reduced dimension. Okay. Note that this approach is essentially the same to our industry classification method as well. Okay, so they define anomalous and then basically they did cluster analysis and they could find a cluster of anomalous transactions. Furthermore, this anomalous detection technique could be used to identify mispriced financial assets like under or overvalued stocks. Hence, intuitively, by combining mispriced assets with a small number of common stock that tends to co-move with their originals, one could generate excess portfolio performance over a benchmark. Again, the idea is simple. Each stocks have a lot of attributes. So again, we have data about stocks, each stock as input, and we have an output about the stocks. And then by comparing the input stock data and output stock data, and then if they are very different, we can regard them outlier stocks. Outlier means possibly underpriced or possibly overpriced. Of course, then we can make money by buying underpriced stock and by selling overpriced stock, right? That's basically intuition. Or we can do clustering analysis of the stock so that we can find portfolio of undervalued stocks or portfolio of overvalued stock. Okay. Hence, intuitively, by combining mispriced assets with a small number of common stock that tends to common with the originals, one could generate excess return, excess portfolio performance over benchmark. So what fund manager does is that the average active fund manager, they usually have a benchmark, and their goal is to beat the benchmark. So the idea is that by combining a stock that is not anomalous, that stock like average stock, and combining that stock with anomalous stock. So using the communal stock that tends to move together with others, that average stock, we use communal stocks to replicate benchmark. And then we use anomalous stock to beat the market. That's the idea. And that is in practice called like a portable alpha. So we have two sets of portfolio. Portfolio one, that is replicate benchmark. Portfolio two, that is supposed to beat the market. And by combining those two portfolios, we can track or benchmark while slightly beating the benchmark. The same idea. Using autoencoder, we find communal stock and anomalous stock and use communal stock to track the benchmark and use anomalous stock to beat the benchmark. And combining that, we can construct a portfolio that track benchmark while beating that. Indeed, Heaton et al. 2017 defined a target return that follows benchmark index but with downside protections. Okay, what Heaton et al. Did is that they have a benchmark and they slightly modify benchmark, like add, if benchmark sometimes lose a lot of money, they can simply get rid of that downside part. Okay, sometimes they can add some fixed amount. Okay, then they add enhanced benchmark. Enhanced benchmark means there is performance better than benchmark. So they have a benchmark and using by slightly modifying the benchmark, they design an enhanced benchmark, and then they developed a portfolio that track the enhanced benchmark. If their strategy is right and successfully track the enhanced benchmark, then by definition, they can beat the benchmark because they follow the enhanced benchmark. Indeed, the Hayton et al. Define a target return that follows a benchmark index but with downside protection, and then construct a basically deep portfolio to replicate the target return. Okay, target return, which is basically IE enhanced benchmark index. The deep portfolios comprises anomalous and communal stocks. In relation, Nakano and Takahashi 2020 construct factors here. Factors in their paper, factors are actually central code in an autoencoder that present downside protection and then replicate the factors with dynamic hedging strategy in order to enhance portfolio performance. Again, Nakano Takahashi. What Nagano and Takahashi did is that they have stocks, and then by making the code as a smaller dimension, they regard this code as a factor and investable portfolio. And then they developed portfolio trading strategy that implemented the code. Actually, it's an attractive code that generates positive alpha excess return.